In this problem, we have a formula for how much a farmer can produce if he utilizes X units of labor and Y units of capital. Now, when you look at this formula, it tells you that's how much it can produce, so that would be our production formula, or maybe productivity formula. And in A, it says find the marginal productivities. And anytime you see that word marginal, you know you want to take the derivatives. Okay. And in this case, derivatives is plural because we do have two different variables. Okay. So for A, let's first find the derivative with respect to x. So we want to take the partial with respect to x. And when we do this, we only look at the x variable and just treat y as the constant. We do not care about it at all. Well, not at all. We still want to be mathematically accurate, but as far as the derivative goes, it's just a constant. We really don't care what it is. Okay, so we have 120 square root of 4x plus y squared. Let's rewrite that as 120 times 4x squared plus y squared. And the square root is really the same thing as to the 1/2 power. Okay, so we take the derivative just like we normally would. So the 120 is a constant, it just stays there. Now when we take the derivative, we take this power of 1/2 and we bring the 1/2 power down. Okay. Now, it's like we had a box, so it's like we're doing the chain rule here. It's like we had a box around the inside. So we're going to keep whatever's inside that box exactly the same. And then, so we brought our power down and we drop our power by 1. So we're to the negative 1/2. Times, now we need to take the derivative of what's inside the box. So what's inside the box, notice once again, we only care about the x. That's the only variable that we care about. So the derivative of 4x squared is 8x plus, now when you try and take the derivative of y squared, remember y is a constant, and the derivative of a constant is 0. So just like if it said plus 7, the derivative would be 0. Now at this point, we could simplify just a little bit. So 120 times 1/2 is 60 times 8, that should be what, 480? So 480 x over the square root of 4x squared plus y squared. Because that was a negative 1/2 power, the negative means bring it to the bottom, 1/2 is square root. Next, it wants to know what this value would be at the point x equals 8 and y equals 12. So we could say at the point 8, 12, now let's plug those in. Or we could use the notation I don't think we'll use any different notation here in this class. So let's plug those into those. So let's do the partial of f with respect to x at the point 8, 12. Okay. So this is going to be 480 times 8 over the square root of 4 times 8 squared plus 12 squared. Okay. We'll put this in our calculator. And we get 192. Now what does this mean? This means that when we have 8 units labor and 12 units capital, then so remember, a derivative tells us slope. And so slope is rise over run, or it tells us if we change x, how much does y change? Or in this case, if we change x, how much does f change? So then if we change x, labor, by 1 unit, then productivity goes up by 192 units. Notice here, I didn't say anything about y. That's because it's the derivative with respect to x. Again, here, it's kind of all we cared about was the x. And so, technically, we're going to say y, or capital, stays the same. So what we're saying is if, okay, we keep capital the same and we only change x by 1 unit, then our productivity will go up by 192 units. So now, that was our marginal productivity. with respect to x. Now we need to do the exact same thing, but we need to do it with respect to y. So we want to find the partial of f with respect to y, and I better write my equation of f down here again so that we can see it. So with respect to y, once again, the 120 is going to stay the same. So our 120 as a constant stays there. Now we need to bring down that power of the 1/2. We keep whatever was inside our box exactly the same. Just like we have a box around everything inside the square root of our 4x squared plus y squared. And we drop our power by 1. Now times it by the derivative of whatever was inside the box. Remember, x squared, or x is just a constant, so it's like we just had a 4 sitting there, and the derivative of 4 would be 0, so the derivative of 4x squared is 0, and derivative of y squared is 2y. So in this case, 120 times 1/2 is 60, times 2 is 1, we're back at 120, y over the square root of 4x squared plus y squared. And now we need to know what that is at the point 8, 12. So right at the point 8, 12. Plug in our x is 8 and y is 12. So it's going to be 120 times 12 over the square root of 4 times 8 squared plus 12 squared, which is 72. So again, this is a partial derivative. This happens in situations where we have two variables and we want to say, well, what happens if we change one of the variables? We can't actually calculate what happens if we change both variables at once, at least not very easily, not in this class. So what we do is we say, well, what happens if we change just one variable? So we'll look at that. So when we have 8 units labor and 12 units capital, okay, because it's different for each specific point, so we do it at one specific point, then if we change y, which in this case is capital, by going up 1 unit, then the productivity will go up by 72 units. And keep in mind that our other variable, x, which is labor, stays the same. Okay. Or you could say if I went up 2 units, then I'd go up by 72 times 2, or 142. And if I went up 3 units, I'd go up 3 times 72, etc. So again, this is telling you if we change just y, then what's going to happen to our productivity. So that was part A. Part B says, let h be a small number. Use our results from part A to determine the approximate effect on production of changing the labor from 8 to 8 plus 8 units while keeping the capital fixed at 12 units. Okay. Or in other words, this is saying, okay, remember what we said when we interpreted it? We said when we have 8 units labor and 12 units capital, if we change the labor by 1 unit, then productivity goes up by 192 units. Now they're saying, what if we don't want to go up by a full unit? What if we want to go up by half a unit? How much should the productivity go up by? Well, if we change x by half, then our productivity should go up by half of 192. Or if we have x go up by 1/3, then our productivity should go up by 1/3 times 192, etc. So it sounds a lot fancier than it actually is. So let's do part B. So if labor, or x, goes up h units, productivity goes up by H times 192 units. And similarly, for part C, okay, we could say if capital Y goes up H units, then productivity goes up 72 times H units. No reason that I wrote H first and H second here, that's just what I wrote it as. Okay. Now let's go back up though and actually look at what C actually asked us. Okay. So C says if you decrease the labor from 8 to 7, what's going to happen? Oh, sorry. It sounds like we're still changing labor, which is X, and capital staying fixed. So let's go back. Never mind, that was not actually pertinent, it was just interesting. I have to read the question carefully. It was still true, it was still interesting, it's just not pertinent. Okay, so now in C, it's saying we want our labor to go down 1 unit actually. So if labor goes from 8 to 7, then it went down 1 unit. So productivity will go down by 192 units. So if it went down 1 unit, that means H was -1. And so our productivity will go down -1 times 192 units, or it goes up negative times 192, which means it really goes down.